Hey everybody, how you doing today? Dr. Heldman here, Tech Talk Education. Have you ever wondered what the difference might be between a conventional classical computer processor, like an Intel or AMD or whatever, versus a quantum computing processor? That's the purpose of this movie. Super interesting stuff. Let's get started. All right, so the subject of this video is classical processors, ARM, Intel, AMD, etc., versus quantum processors. Now, these processors, quantum processors have to work in the quantum mechanics area versus classical processors. Let's find out what the difference is between these. So first of all, a conventional processor, and I'm going to call that a classical processor. Every laptop, server, phone, they all have in them what's called a classical processor. These are built from billions of tiny switches. They're called transistors. And the idea is that a transistor can either be turned on or off. So if it's turned on, it's given a 1, it's binary 1. If it's off, it's binary 0. This is how the binary language is formulated. This has been this way since processors have been around. So this is the idea behind a conventional classical processor. However, a quantum processor works a little bit differently. Quantum processors use what is called a qubit, a quantum bit, and it's short for quantum bits. A qubit isn't just a 1 or a 0. It can be a 1, a 0, or both at the same time in a state in what is called superposition. Qubits can also become entangled, which means that the state of one qubit depends on the state of another, even at a distance, even at a great distance. So quantum computers have a huge edge because they can be in a lot of different places all at once. Now this thing here in front of you is called a Bloch sphere, and this is something that you'll have to get used to when it comes to working with qubits and understanding how they work. And you're going to see a little notation here. I've got a diagram I'm going to put up on the screen and talk about here in just a minute. But you can see here that there is a diagram where you have the pipe symbol, a 0, and then a right angle here. This is called a Ket, K-E-T. And it's taking its terminology from what's called Bra-Ket notation. And Bra-Ket notation was invented by a guy named Dirac, D-I-R-A-C. So what it's telling you here is that this thing is at the 0th position here at the top. It's at the 1th position at the bottom, but it could be anywhere in between these things. And so it's going to be important to get the idea of a Bra-Ket terminology down as you go forward. This is what the Bra-Ket notation looks like. It takes its word from if I have a left angle bracket here, and then I have a series of numbers here. This is called a vector. A vector is just a series of numbers in a row like this. It could be very large, very long, or very short, like in this case. And then a right angle, a right pipe. Now this is called a bra. And what that means is that the bra is horizontal. The ket, on the other hand, has a pipe symbol here, and then your vector, and then a right angle bracket. This is called a ket. And in this case, what happens is that it is a vertical vector, not a horizontal vector. So the main thing to remember here, you'll have to remember this notation. You'll see it quite frequently. It's used very commonly in quantum mechanics and in quantum computing. If you see a left angle first and then a pipe, you know you're looking at a bra, even though it doesn't say bra. If you see a pipe, then a right angle, you know you're looking at a ket. Then the other thing you have to remember, and you probably need to snag a class on linear algebra if you've not. There are some good books, good YouTubes out there, some not so good YouTubes. But if you're looking, you need to learn linear algebra, and you need to understand that when we're dealing with vectors, a vector can be put on its vertically like this, that would be a ket, or horizontally like this, that would be a bra. And you will use this terminology extensively when you're working with quantum computers. Now here's how the two differ. So we have a table here, the feature, the classical processor, the quantum. The unit of data for a classical processor is a bit, 0 or 1. There are 8 bits to a byte. There's some old terminology, it's called a nibble. There's 4 bits to a nibble. And then the quantum processor it uses a qubit, which could be position 0, position 1, or somewhere in between. Processing power for the classical processor is linear, but here's the thing that makes quantum processing so great: it's exponential, and so it can solve problems much more quickly than a classical processor can. When we get above the point where we're dealing with 100 qubits or more, this isn't my terminology, I took this from a quantum class I've been going through. Once you begin to exceed that 100 qubit limit and you move up, now you're in the area where only quantum mechanics can solve, quantum processing can solve certain processes or certain problems. And so now we're seeing 133 qubit processors, 156 qubit processors. So the companies that manufacture these things keep growing. Now, another thing you'll need to know about with quantum processing is that in the classical processor, you use what are called, you have transistors that are either on or off, and then the way that we make decisions about how the data flows, the electricity flows, is we use what are called logic gates. Now, in a quantum processor, we use qubits, superposition, and entanglement, but the same idea of these gates, letting electricity flow a certain way or another, is still there, but now we turn it into quantum gates, and it's quite a bit more involved than just the logic gates. And if I'm being honest with you, the logic gates are pretty involved too. So the strengths of a classical processor are they're well known, of course, general purpose, very, very stable. Everyone knows about them. The quantum processor brings about what is called massive parallelism for specialized tasks, meaning that we can run these jobs in parallel. We can make much faster decisions. This is going to be especially helpful in cryptography and in creating cryptographic algorithms that are airtight, that cannot be cracked. The other side of it is that quantum computers can theoretically crack conventional cryptographic algorithms very, very rapidly. So there are lots of people in the security game that are worried about that. Weakness of the classical processor is that it hits its limits with complexity. So the more complex a problem gets, the more we're going to use that processor, the busier it's going to get. It's going to take more time to get the job done. The quantum processor is fragile. It has to be kept at near absolute zero temps. It's error prone, and of course it's expensive. You're not likely to have a quantum processor laptop anytime soon. Now, the challenges of quantum computing, this is an actual IBM quantum computer. Quantum computing is not magic. It's still in its early stages. You should be aware of that. I think that's why this is a very good career move for you, to understand how these things work. Because once they get put into the mainstream of things like the stock exchange, cryptographic algorithms, things like that, very, very difficult to solve problems, they're going to really grow once we prove that they're useful. Qubits are fragile. They're easily disrupted by temperature, noise, or even cosmic rays. That's why most quantum processors are kept in supercooled environments that are colder than outer space. They're near absolute zero. Also, quantum processors don't replace classical ones. You shouldn't think about, I'm going to run out and buy a laptop with a quantum processor in it. You're not going to do that anytime soon. This is big boy stuff in cloud-based environments. However, all of the big players, the IBMs, Microsofts, Oracles, I don't know if Oracle's playing in this sandbox or not, AWS, Google, all have cloud-based quantum environments, and you can get into it and start working with it for free. I'm on the IBM cloud, and I'm really, really enjoying learning about this technology. Now, it's best for certain use cases. You can think of this as a new tool, not a universal replacement for classical processors. Now, there's some real-world examples. I'm going to put some websites down in the show notes here in a minute. But today, the big players are IBM is very, very big in this arena. Google is huge in this. They're doing a lot of work. Intel, of course, which makes normal processors. They make classical processors. I was just reading about a new one that they're thinking about releasing pretty quickly for gaming computers. And then there's a really interesting company called Rigetti that's out there that's doing some work like this as well. These guys are all racing to build usable quantum processors. And you can use this for things like drug discovery. This is going to be very appealing to pharmacological outfits that are researching new drugs because, as you might imagine, very, very complex to look at over the entire biosphere and the chemical sphere and figure out how things go together in order to make a drug that might be really, really effective for certain diseases. It is going to be used in material science for sure, because we figure out ways to create new materials or enhance them or strengthen them, whatever. It'll be used in cryptography and then in optimization problems. We're still years away from full-scale commercial use, which is why I preach to you again. I think this is a good time to begin investigating, getting into it. Now, how to get started. So if you're interested in learning more, and I will put the URLs down in the show notes for all this, you don't need a PhD to explore quantum computing. As you're out looking at YouTube videos, you're going to see a lot of PhDs talking about quantum mechanics. Some of them are, as you might imagine, pretty boring people that this is not their bailiwick to get up and stand in front of a mic and a camera and talk about these. So it's pretty dry material, and they can be pretty dry people. I'm just going to warn you, but there's a lot of videos out there about things like Bra-Ket terminology and quantum mechanics. It's a fascinating, fascinating field. Now, here's some places to get involved. IBM's Quantum Lab is super good. That's the one I'm engaged with. There is a Qiskit textbook. You should be aware that IBM created a language that allows you to write a script that will run on a quantum processor. They've made it for Python, and they call it Qiskit, but there's also a thing called QASM, Q-A-S-M. So if you know how to write assembly language, you could write in assembly for the quantum processor rather than with Python. And then, of course, Microsoft has what's called the Quantum Caddis, and there are a couple of really good books that I think you might enjoy. I'll put the links to those out there as well. Okay, did you enjoy this video? I just wanted to continue to talk a little bit about quantum processing. This is positionally where AI was just a few years ago, where it was sort of an immature field, but there's a lot of buzz about it and researchers keep going. This is where we're at now. So we're really in a good green field with quantum. Might be something that you think about getting into to enhance your career, or at least be able to be on a talking basis with people that know about this. Super interesting material. If you enjoyed this video, please like it and share it with others. Please like my channel. I would love it if you would subscribe to my channel, share it with others. I am trying to grow the channel. And then you're welcome to drop off comments anytime you like about any of these movies. I get some super good comments, guys. I really appreciate it. Thank you for that. And I will talk to you in the next video. Thank you, and have a great and wonderful day.